All right, good night, good evening, everybody. We're going to talk about water tonight. Feel free to fast forward to whatever section you need to fast forward to and listen to it at a sped up rate if that makes it easier for you. I think I talk pretty fast, but if it makes you go through the notes a little bit faster, that's awesome. All right, let's go ahead and talk about water. Water is a huge, incredibly important deal on our planet. And the question is, why is it such a big deal? Why are scientists looking for water? Oops, my picture's covering it right now. Why are scientists looking for water on other planets? Why does it matter? And there's this headline here: proof water ice found on Mars. Water ice? What other ice is there? Well, there's lots of other different types of ice, and so it's really important that this is actually ice that is made from water. Scientists so far, all life as we know it requires water, and they actually believe that any life that we're going to find anywhere else in the universe, nothing like humans, that's totally fine. It's still going to require water. And the question is why? What is so special about water? Why do they think water is necessary for life to be on a planet? So that's what we're going to be looking at today. So again, it says water is needed for life. And I like this little graphic that shows the distribution of water on this planet. Most of our water is found in the oceans. There's just a tiny amount of fresh water. Fresh water is becoming a bigger and bigger concern on our planet as we have a larger and larger human population who needs that water, and global warming causing more and more of that water to evaporate, pollution causing it to be polluted. There's a big concern that we're going to be starting to see more and more armed conflicts over fresh water. It's kind of ironic that we live in a state known for its freshwater resources. So how that will play a role in the future is a very interesting question. So Earth is incredibly unique in the universe for its amount of liquid water. 71% of the surface of the planet is covered in water. The chemistry of life is what we call a solution-based chemistry. And what that means is that all these chemicals that your body uses, all these reactions that are happening in your cells, they're all happening within the base of water, and water is dissolving all of these molecules. And so we call it a solution-based chemistry. The majority of any organism is made up of water. And finally, water is one of the few substances that exists in all three phases at normal terrestrial temperatures. So what that means is that we have ice, we have liquid water, and we have water vapor all present on this planet. Those of you that are interested in astronomy maybe have heard about the Goldilocks zone that's named for the area around the sun where a planet could have water in all three phases. And the Earth is in the Goldilocks zone. And so scientists are searching throughout our galaxy for planets that are orbiting suns that give off similar amounts of radiation to our sun. So it's very specific areas of the galaxy that might fall within the Goldilocks zone where they would have especially liquid water. Liquid water is incredibly important for the possibility of life. All right, let's move on. Let's talk about water's unique properties. The first thing that I'm going to recommend, if you haven't done so already, is to make this diagram, to draw this out. You should be able to draw this picture. So what we have here are 4 water molecules, 1, 2, 3, 4, 5 water molecules. I'm good at counting. And the dotted lines are showing something that are called hydrogen bonds. And hydrogen bonds are very weak bonds that form between the negative section of one water molecule and the positive section of another water molecule. Now that's hydrogen bonds don't only occur in water molecules, so I don't want to make that impression. But they're especially important in water molecules. So off to the side, it says these hydrogen bonds are weak, super weak form of a hydrogen or form of bond. However, when you have a large body of water, there are so many hydrogen bonds that they end up creating really important characteristics or properties for water that make water different from other liquid elements. There are so many unique properties, and they're all due to the polarity of water and its resulting hydrogen bonds. You don't need to write this down yet. They're going to come up in the next slides. Cohesion, adhesion, surface tension, capillarity, high specific heat, evaporative cooling, the fact that ice floats, the fact that water can can dissolve so many substances, and the fact that water can dissociate, and we'll talk about what pH is. Those are all super, super unique properties of water, and why we think water is necessary for any life on any other planet, and especially important for life on this planet. All right, so let's introduce you to the terms adhesion and cohesion. So cohesion and adhesion are two words that are super easy to mix up because they sound exactly the same. I'll give you a little hint to remember them in a minute. So cohesion is the sticking together or the attraction of the same molecules, and it's due to their polarity. Water is highly cohesive. It's very, very attracted to itself. The spider is able to walk on the water because the hydrogen bonds between the water molecules lead to high surface tension. If there weren't those hydrogen bonds pulling the water molecules together, that spider would sink right through. But water has high surface tension because of cohesion, because those water molecules are sticking together. Adhesion is a similar property, but instead of sticking to each other, they're sticking to different things. So adhesion is the attraction of usually polar molecules to other polar molecules. So polar water molecules adhere well to other polar surfaces like glass, and we're going to look at the image on the left in just a second, or cell walls during transpiration, which we're going to see in the next slide. Notice in the diagram that mercury is not polar. So what we see in the diagram to the left are an image of water and an image of mercury. In the image of water, we have two, and those are supposed to be glass tubes. One of the glass tubes is thicker, has a wider diameter, and one of them is thinner. Notice the meniscus, that's the curved shape of the water. What's happening as the water gets close to the glass is that it starts creeping up the glass because the glass is polar and the water is polar, and so they're attracted to each other. And so it is actually possible for the water column to defy gravity a little bit because of its attraction to the glass. However, if the water column is heavy enough, gravity will keep it pulled down. If you have a thin enough glass tube, like the skinnier one here, the water is able to creep up at higher and higher, and it's able to defy gravity because the polar attraction is greater than the force of gravity pulling on it if it's a very thin column of water. Now compare that to the mercury. The mercury is not attracted to the polar surfaces of the glass, and it does not defy gravity. It doesn't pull itself up the glass in the same way. All right, so I was going to give you a quick tip about how to know the difference between cohesion and adhesion. I think this is kind of a lame way to remember it, but when I think of the word co, I think of co-workers. And so when I think of my co-workers, they are people that do the same job that I do, not my boss, not my customers or my students. Co-workers are the people that do the same thing that I do. So cohesion is attraction between molecules that are the same. Adhesion is attraction between molecules that are different. So why is and then we already talked through this. Capillary action, let me get my image out of the way here. There we go. Capillary action is due to adhesion of the liquid to the tube and cohesion of the liquid to its own molecules. So as the water molecules are creeping up the glass tube, they're carrying with them the water molecules that are close by. So it allows it to move against gravity, stopping only when the weight of the liquid column overcomes the forces of cohesion and adhesion. Now that completely ties into our next concept, super important in biological processes, and that's the idea of transpiration out of plants and trees, which are a type of plant. Transpiration is the upward movement of water. Have you ever thought about how incredibly crazy it is that water moves from roots to leaves? Have you ever taken a second to think about that? Water is crazy heavy. Have you ever tried carrying a gallon of water? It's heavy. Plants, especially these giant trees, the giant sequoias and the redwoods, they're carrying a swimming pool's worth of water and they're lifting it up. How does that kind of magic happen? Well, first of all, the transpiration, that's what it's called. It's when this water is moving upward and then evaporating out of the leaves. And remember that needles count as leaves, just they're a modified type of leaf. All right, so the whole process is powered by the sun. As the sun heats up the leaves and the air around it, water starts evaporating from those leaves. Notice also this very important, we're going to talk more about water potential in the next unit. Notice this blue arrow along the side of the tree. That's called the water potential gradient. There's more water near the roots and there's less water in the air near the leaves. Water is going to travel, it always does, and we'll learn about this, from areas of high concentration to areas of low concentration. So the water is more concentrated near the roots and it's less concentrated near the leaves. So it's going to want to travel in that direction. But the question is, how is it traveling against gravity without a pump or a heart that's pushing it upward? So evaporation of water molecules from the leaves, it's powered by the sun, causes the water molecule, as each water molecule escapes from the leaf, it is attracted to the water molecule that was next in line. So it tugs on the water molecule that was next in line. We call that cohesion. So transpiration involves cohesion and adhesion. Some of those water molecules are attracted to the cell walls of the tubes in the tree that are called xylem. So you'll see them in this diagram here. It says xylem cells. Xylem cells are those really skinny, like capillary tubes that we talked about on the previous slide. They're really, really skinny tubes that carry water from the roots up to the leaves. So the water molecules are attracted to each other and they're attracted to the walls of the xylem. So as the sun evaporates a water molecule out of the leaf, that water molecule tugs on the water molecule that was next to it and pulls it up. And that water molecule tugs on the one that was below it and pulls it up and tugs on the one that was below it. And they're all tugging on each other, pulling themselves up. It's a pretty cool process and super important to life on this planet. The other thing that you should know about transpiration that is super fascinating is that large amounts of transpiration, so in forests, especially in rainforests, they can actually change weather patterns. So in our rainforests, the plants, the trees, are transpiring so much water into the atmosphere that they're actually causing the rain of a tropical rainforest. So the question becomes, what happens when we cut down the trees? So as we cut down trees for farming, not just in the United States, but in many of our areas of the world, as farmers are cutting down trees, they're actually changing the weather patterns. And that is profoundly concerning, even if we were to tell them, stop, you need to plant trees, don't cut down your trees. If they plant trees, the weather patterns have already changed, so the rain won't come back right away. And so it takes hundreds of years for those trees to start growing back and for those weather patterns to return. So definitely something we need to be watching for as we try to take care of this planet. All right, the next unique property of water has to do with its high specific heat. So we're going to learn more about this in chemistry during term 4. So what is specific heat? It's how much heat is absorbed or released before there is an increase in or a decrease in temperature. So if we have, let me give you 3 examples. So if we have water and we add heat to water, it takes lots and lots of heat added to water before the water warms up. Think about how long it takes you. This is maybe a good example. How long does it take you to boil a pot of water? If you touch the pot itself, the pot is like burning hot, but the water on the inside might not be hot at all. That's because the specific heat of the water is extremely high, and it takes much more energy to get the water to heat up than it does the pot. So take a look at these comparisons. Water has a really high amount of energy. It's measured in joules per gram degree Celsius. Again, we'll learn more about this in chemistry in term 4. Ethanol only requires 1.24 joules per gram degree Celsius, which means it only needs 1.24 joules of energy to raise the temperature 1 degree Celsius. Iron only requires 0.449 joules for every 1 gram to move it up 1 degree Celsius. So it's much less energy is required for it to heat up. Well, how does that impact our planet? Lots of different ways. The reason that water has such a high specific heat is because of all those hydrogen bonds. I told you these are important. They're very weak bonds, but they make a big difference in water's unique properties. So on this planet, the reason high specific heat matters is that we're covered in water. This planet is 71% water, and that water acts as a temperature buffer. So as the temperature increases and decreases on the planet, the water, the oceans stay pretty much the same temperature. And that moderates temperatures all over the planet. So it takes an enormous amount of energy to change the temperature of the ocean. Here's the bad news, ladies and gentlemen. What's happening to our planet right now? Global warming. So this is a quote that I took from the EPA, the Environmental Protection Agency from the United States. So it says, sea surface temperature has increased during the 20th century and continues to rise. From 1901 through 2020, temperatures rose at an average rate of 0.14 degrees Fahrenheit. We usually use degrees Celsius in science classes, but whatever. So per decade, the temperature of the ocean has been increasing, and the increase in temperature of oceans has definitely been a factor in the death of coral reefs around the world. All right, another factor that's important with high specific heat is the concept of evaporative cooling. So this information on the left side is all the same. So it says organisms rely on something called heat of vaporization. That's the energy required to turn a liquid to a gas. So look at this person's face. They're sweating. They have liquid water all over their faces. It takes energy to move from being a liquid to a gas. And that process of moving from liquid to gas releases heat into the environment and cools the person. And so that's one of the super important ways that animals and life on this planet keep itself cool is by the process of water evaporating and cooling their bodies. All right, the next important property of water is the fact that ice floats. You've probably never given this much thought, the fact that ice floats, but you guys, solids don't usually float. Solid water is less dense than liquid water. Usually solids are more dense than liquids. So the question is why, and you definitely need to be able to say this. You need to be able to draw this. You need to be able to wrap your mind around this. The crystal lattice. So take a look at the two diagrams here. This is the crystal lattice here. The crystal lattice that forms because of the hydrogen bonds is stable in ice, and it's spacious. The hydrogen bonds are set far apart from each other. In liquid water, those hydrogen bonds, it's moving around, the water molecules are moving around, and so the hydrogen bonds are constantly being formed and reformed. And so the water, look at the two diagrams. Do you see how the water molecules are closer together? It's more dense. It says here, as water cools, its kinetic energy, and maybe some of you remember that that's the energy of motion, the kinetic energy decreases, it goes down, and the hydrogen bonds become more stable. As ice forms, the hydrogen bonds cause the water molecules to space out in a crystalline form, and that spaced out crystalline form is less dense. So that allows ice to float. Well, so what? What would happen if ice were more dense and it sank to the bottom? So ponds, lakes, and oceans would freeze solid, killing life below. And I'm showing an image here of widow fishies under the ice. Floating ice reduces heat loss from the water. So right now, that ice that's on the top, it's preventing heat from being released from the water below. So it's actually keeping the temperature of those fishies and their environment a little bit warmer. The water below is unlikely to freeze to the bottom. If the ice sank, the water would be constantly pushed upward and its heat would release into the environment, and eventually it would freeze solid. And so that's another characteristic that allows life on this planet. All right, water is a great solvent. We said it's the universal solvent. It's a little exaggerated, it's not universal, but water is super, super good at dissolving molecules because it's polar. It can dissolve anything that are ions. Now, remember, an ion is something that gained or released electrons. And so that means it has a full positive charge or a full negative charge. Anything that's got an ionic charge is attracted to water. In addition, anything that is polar also is attracted to water. So water can dissolve substances like salt, like sodium and chlorine. It can dissolve other polar substances like sugar that might be found in blood or plant sap or cell cytoplasm. It can even dissolve, this is a wacky thought, large nonpolar molecules. So this diagram over here, that's a protein, and proteins are nonpolar. However, proteins are enormous. We're going to learn all about them. And sometimes they have polar areas on the surface. And so those water molecules can be attracted to the polar areas, and then that helps them dissolve the proteins. So water is really pretty amazing. All right, the last topic, and this is maybe the trickiest topic, unfortunately, we are going to have an acids and bases unit, term 4, so it'll all come around and you'll start to get more comfortable with it as we go. I'm just going to give you an introduction to acids and bases and pH right now. So water is capable of coming apart. It's called dissociation, and that's due to the fact that it is a polar molecule. So water can break. Normally we have H2O, but it can separate into hydrogen ions, H plus ions, and hydroxide ions, OH minus ions. Now, there's a whole bunch of things you need to know. Hydrogen ions are just a single proton. What? I don't get it. Think about it for just a second. Hydrogen is number 1 on the periodic table. That means it has 1 proton and 1 electron. Notice that it's H plus. The reason it's H plus is that its electron has been taken away. So if all it had was a proton and an electron, and that's hydrogen, and we took the electron away, that means that all hydrogen ion is a proton. So those two terms are interchangeable. So if somebody says it's a proton or if somebody says it's a hydrogen ion, they're talking about exactly the same thing. Now, to make it more complicated, sometimes they'll even refer to hydrogen ions as hydronium ions when it comes to talking about water dissociating in pH. Look at bullet point number 2 here. Hydrogen ions immediately react with intact water molecules to form what are called hydronium ions, H3O+. So when water comes apart and forms the H plus ions and the OH ions, the H plus ions, was it this hand? The H plus ions immediately are attracted to water molecules and stick to it. So that's what you see in this diagram here. We had 2 regular water molecules, and then we had 1 water molecule break apart. And so there's the OH from that 1 water molecule, and the hydrogen from that 1 water molecule immediately snapped onto a water molecule. And so now we have H3O plus and OH minus. In pure water, the concentration of hydronium ions and hydroxide ions is equal. And that's going to be important in just a second. So let me show you this on this screen. I have this number, 1 times 10 to the negative 7 moles per liter. I have that written in the corner just so I can reference it in just a moment. So pH is what we're getting to. pH is a measure of how acidic or basic a solution is, a substance is. And you calculate pH using a kind of weird equation. So pH is equal to the negative log, now not everybody remembers what logs are, we'll get to that, of the hydronium ion concentration. It can also be written the negative log of the hydrogen ion concentration. The brackets, those square parentheses, those are called brackets. Those literally mean concentration of. So when I read this equation for pH, it is the negative log of the concentration of hydronium ions. Okay, so that's how you calculate pH. So let's try this. Because pH is based on a negative logarithm, before I go any further, let's remind you what a log is. So let's practice that really quickly. If I have a number like 10 to the fourth power, so 10 to the fourth, the log of 10 to the 4 is 4. It's whatever that exponent is. So if I have another number, 10 to the 27th power, then the log is 27. And if I have, let's look at this number that I have up here. If I have 10 to the negative 7, 1 times 10 to the negative 7, the log is negative 7. Now, pH, the equation is the negative log. So let's try that again. If I have a number 10 to the fourth and I want to do the negative log, then it would be negative 4. If I have 10 to the 27th and I want the negative log, it would be negative 27. Just bear with me. So if I have the number 1 times 10 to the negative 7 and I take the negative log of that, then that would be 7. The negative log of 10 to the negative 7 is the whole number, or the positive number, 7. So this is where pH is a scale that runs from 0 to 14. And 7, there's the number 7, 7 is considered neutral. When water breaks into hydrogen and dissociates is the word, when water dissociates into hydrogen and hydroxide ions, the concentration of hydrogen ions or hydronium ions is this number right here, 1 times 10 to the negative 7 moles in 1 liter. So when I take the pH of that, the number is 7. So pure water, that's what number 7 is. Pure water has a pH of 7. Let's try it again, just something totally different. Let's say I had a substance and the concentration was 1 times 10 to the negative 2. Well, the negative log of 10 to the negative 2 would be 2. So the pH would be down here, and that would be an acid. Okay, so now let's go back to this bullet point. It says, because pH is based on a negative logarithm, the concentration of hydronium ions is inversely proportional to the pH. Just trust me on this. So listen to what that means. When the concentration of hydrogen ions increases, when there's more of them, the pH is decreasing. When the hydrogen ion or hydronium ion decreases, when there's fewer of them, we say that the pH has increased. So down here, if I look at a pH of 1, then we say there's lots of hydrogen ions. But with a pH of 14, we say there's not very many hydrogen ions. And remember that hydrogen ion and hydronium ion are interchangeable sort of terms. Okay, so acids are substances that donate protons, hydrogen ions, remember all these words are the same, to water. So let's imagine hydrochloric acid. It has a hydrogen in it, and so when I dissolve hydrochloric acid in water, it's adding that hydrogen. It's also adding a chlorine atom as well, but it's increasing the number of hydrogens in the water, and so there's a greater number of hydrogen ions. So it has a high hydrogen ion concentration, so that means it has a low pH. Bases are the other way around. They actually suck up hydrogen ions out of the environment. So that means they have not very many hydrogen ions in the environment. So that means they have a very high pH. So it's the opposite. So that's called an inverse relationship. All right, last thing that we want to talk about, this is our very last page, and this is maybe, if you remember anything from all these notes, this is what I want you to remember because it's super important to our world right now. pH and biology. Biological systems can only tolerate a very, very narrow range of pH. If you've ever owned fish, if you buy fish at the fish store and you just dump them into your water, your tap water at home, there's a very good chance that those fish will die within a matter of hours. And that's often because the pH from the fish store is not the same as the pH of the tap water in your home. And the tap water is often not at pH 7. That's what distilled water would be when there's only water in it and nothing but water. Okay, so they can only tolerate a narrow range of pH. Extreme variations in pH have bad effects at all levels of organization. So all levels of the environment are affected by changes in pH. Note this extremely important reaction that's on the left here, and please remember the gist of it for the rest of your life. I don't need you to remember the equation for acetic acid specifically, or the molecular formula for acetic acid, but I want you to understand what you're looking at. What is the reaction showing exactly? So we've got carbon dioxide plus water is making an acid. Well, okay, why is carbon dioxide important on our planet right now? And hopefully you're all thinking, well, global warming, right, KJ? Indeed. As carbon dioxide increases from the burning of fossil fuels, look at this airplane flying by and it's releasing carbon dioxide into the atmosphere. As the ocean waves capture some of that carbon dioxide that's in the air around it, the carbon dioxide and the water mix and they form acetic acid. So not only does it lead to global warming, carbon dioxide, it also leads to ocean acidification. So we said earlier that as the planet is warming, the temperature of the oceans very gradually, because it has high specific heat, those oceans are increasing, and that's killing our coral reefs, which is the foundation for all environmental systems in the ocean. That's the bottom of the food pyramid or the food web, are their coral reefs. So they're getting damaged by the increase in temperature of the oceans, and they're getting damaged by ocean acidification, where the pH is decreasing over time, and that's damaging our coral reefs. Okay, ladies and gentlemen, that's it. I hope you all have a good rest of your day. Let me know if you have any questions.